In this example, I'll show you how you can do a two-sample z-test for proportions when you're just given the basic information. Given the following information, calculate the z-test statistic, p-value, and state whether or not to reject the null hypothesis based upon our significance level. So first of all, if we look at the null and alternative hypothesis, we can see that we have two proportions, which implies that we should do a two-sample z-test for proportions. And it's also a upper one-sided test, and that's because we are asking, the question of interest is whether or not P1 is actually greater than P2, and we can then denote that with this alternative, where P1 minus P2 is greater than 0, meaning it's a positive proportion or positive value. All right, so what this means is that we'll get an upper one-sided test, which means we'll have an upper one-sided p-value. All right, so let's go ahead and set up our sample proportions. So p hat 1 is equal to x1 over n1, which in this case is equal to 18 over 30, and this is equal to 0.600. And p hat 2 is equal to x2, so the number of observations in the sample that has the characteristic that we're interested in, divided by the sample size, so that's 11 over 26 for the second population sample, and so that's 11 over 26. This comes out to be 0.423. All right, just as a side note, it's really important to carry your decimals at least 3 to 4 decimal places when doing proportions tests, because slight differences from rounding can really change your answer. So it's important to carry a lot of decimal places when you're doing proportions problems. All right, and so the last thing we should do is we should calculate just the pooled proportion, so p hat. This is basically what we would assume the null hypothesis to be true. So when P1 is actually equal to P2, then we assume that P hat would be then the proportion in both populations. So we basically just take our two sample successes, so 11 plus 18, and divide that by their sample sizes. So in this case, that's 11 plus 18 over 26 plus 30, so x1 plus x2 over n1 plus n2, and this is equal to 29 over 56, which altogether our pooled proportion is 0.518. We need this for our test statistic. All right, so if we want to calculate the z-test statistic, this is equal to p hat 1 minus p hat 2 minus 0, that's our claim value, divided by the square root of our standard error of our statistic, which in this case is p hat 1 minus p hat times 1 over n1, 1 over n2. All right, so now if we want to just plug in the values that we got from over here, we find that z is equal to 0.600 minus 0.423 divided by the square root of 0.518, that's the pooled proportion, 1 minus that, 0.518, all times 1 over 30 plus 1 over 26. So what we get for our numerator, then if we continue to calculate this, we get our numerator value to be 0.177, and we divide that by the square root of 0.0179. So the stuff that's in the middle here, or under the square root, comes out to be 0.0179 approximately. And then this is equal to 0.177 divided by 0.1338. This gives me a z-test statistic of 1.32. All right, so I'm not quite there yet. I've got my z-test statistic. Now I need to find the p-value. Well, I know that a z procedure means that my z-test statistic is going to come from a standard normal distribution or standard normal table, and that is referred to as z. So basically we know that this is centered at 0. Most of the data is between 1, 2, and 3 standard deviations from the mean. And if I kind of draw in where my test statistic is, it'll be about right here. This is 1.32, and I want to find the value that is greater than 1.32, and the reason why is because we again are doing an upper one-sided test. Why? Because this is asking a greater than. So this is going to match our alternative. Our p-value will always match the alternative hypothesis. So it's a one-sided upper p-value. So now we just need to look for this value up in the table. So if we go over to the table, we can scroll to our z-test statistic. We can see that we have 1.3 right here, and we cruise across until we find the 0.02. We find that our p-value then, or the area that falls below our z-test statistic of 1.32 is 0.90658. This is not the p-value yet because this is the area that falls below our test statistic, so 0.90658. We come back over here, we see that this is this area, 0.90658. This is not the area that we're interested in. We're interested in the upper value, so this is just 1 minus what we get from the lower, which is equal to 0.09342. So that's that area. This is our p-value. Our one-sided p-value is equal to 0.09342. Now, if we compare this to our significance level, which is 0.05, if we look up, make sure that's right. Yep, significance level, alpha was equal to 0.05. If we compare our p-value to that, we know that this is larger. So our p-value is larger than our test statistic. So if we look at this scale, this is alpha 0.05. Our p-value is up here at 0.09342. And this is the area where we're going to fail to reject the null hypothesis because it's larger than our significance level. If it was lower than our significance level, then we would reject, but our p-value is a little bit larger than that. So we're going to fail to reject the null hypothesis. And a p-value of 0.09342 is not really large, but it's still somewhat small enough to where we could say, but they're suggestive, but just inconclusive evidence in this example that p1 is greater than p2. So even though our p-value is small enough to make kind of suggestive evidence in favor of the alternative, our p-value is not small enough based upon our cutoff to reject the null hypothesis. So we're going to fail to reject the null in this example.